Hello students, welcome to the second lecture on MA 280, that is programming with MATLAB. Now under this chapter we shall be looking at matrix operations where we get to perform some very basic operations using MATLAB, okay? And with this we shall dwell on the knowledge you guys gain during your linear algebra course in first year, okay? So let's before we get to that aspect, let's see how we can generate some sequences or create new variables or new entries once it comes to MATLAB. Okay, now in MATLAB we can create a sequence of numbers using this syntax, that is a colon b colon c. Okay, where the a will refer to the starting value, b will be um, the level of increment, and c is going to be the ending value. Okay, so note that if we like to create a variable or create a sequence of what numbers starting from 0 up to 20 with an interval of what 2, we could use 0 colon 2 colon 20. Okay, so this is just going to generate numbers from 0 up to 20 with an interval of what 2 2 2 2. Okay, so in that same case, if we like to create a sequence of numbers from 0 up to somewhere like 100, we could make use of, let's say, 0 up to 100 with an interval of, let's say, 5. We could just specify that up to 100. Okay, so once we hit enter, they're just going to create the numbers for us. Okay, so bear in mind that the first one happens to be the starting value, the middle one happens to be the level of increment, and the last one happens to be what the value. Okay, so with this, just as we demonstrated in lecture 1, you can also create an array of numbers using this sequence that we have. Okay, so remember that in MATLAB, if you want to create an array of numbers, you have to use what the block parenthesis. Okay, so that is also that. So in this case we are creating this string of values from 0 up to 40. Okay, and we are assigning everything to a. Okay, now this array that we are creating here could simply be created using this sequence that we just talked about. Okay, so we can start from 0, end at 40 with an interval of what 5, and that is just going to give us the same output that we have here. Okay, although this is going to be a little bit lengthy, we can shorten it using this sequence notation. Also, we could also use a special function called the linspace. Now with this linspace, we can create an array with n number of equally spaced starting from this point A and ending at B. Okay, so suppose that we like to generate numbers starting from 10 up to 20, but in that we need only 5 outputs, such that these outputs they will be equally spaced. Okay, so in this case we could use the linspace function, specify the initial starting point or the starting point and the end point, and specify the number of let's say values that we need in this. Okay, so in this case, using the linspace 10, 20, and 15, this is just going to provide us with 5 numbers, but these numbers will be equally spaced. Okay, so you can see that from 10 up to 12.5 we have a difference of 2.5. From 12.5 to 15 we have a difference of 2.5. So that will exist throughout to the last entry. Okay, also if you like to generate numbers, okay, that are spaced equally based on their logarithms, we could use the log space just as we use the length space. In this case we could use the log space. Okay, so this is also going to generate 4 numbers. Okay, and they are equally spaced being based on their logarithmic values. Okay, so in this case we are starting from 4, and this should give up to the fourth logarithm, okay, and we need what, only what, 4 numbers in right here. Okay, so let's see how we get to perform our matrix operation, that is the simple addition, the subtraction, and the others. Okay, now suppose that we create two matrices, that is matrix A and B, where matrix A having to have its inputs to be 12, 8, 5, and 15. Matrix B also having 10, 4, 8, and 12. Because this matrix, two matrices could be added, we can just add them using what, the function A plus B. So once we type in A plus B in MATLAB is just going to add these two numbers, okay, in the form of element wise. Now you could see that in this case it's just going to take the first entry and just add to the first entry of the matrix B. Okay, so 12 plus 10, that gives us the 22, 8 plus 4, that is the 12, and the remaining what, continues. Okay, also we could do same, or we could also subtract these two matrices. So we have A minus B, and that is exactly the output that we are looking for. Okay, we could also think of what, multiplying two matrices. Now remember that before you can multiply two matrices, it means that the number of columns in the first matrix should be the same as the number of rows in the second one matrix. Okay, but because this is a row vector, that rule does not apply here, meaning that if we like to perform any multiplication, we have to do it what, element wise. Okay, so in this case the first input is just going to multiply the first input of the second matrix. Okay, so 12 times 4 giving us the 48, 8 times 4 giving us the 32. So that is how the element wise multiplication is being done. Okay, now in the same case we can perform element wise division. Okay, so this is just going to divide the 12 by 4, 8 by 4, and that is exactly what we have down here. Okay, now in that same case we could also multiply any vector by a scalar. So in this case, with our vector that we have, that is the matrix A, and our scalar, suppose that we like to multiply the whole of matrix A by 5. Okay, you create a new variable and assign this 5 to this new variable k. So once we multiply k by the vector A, that is just going to give us the multiplication of that vector. Okay, so in here the results that you see here is from 5 times 12 giving us 60, 5 times 8 giving us 40. Throughout 2 we get to the last point. Okay, in that same case we could do this element wise, but that is basically the same thing. Okay, and that is exactly what we have down here. Okay, now let's get to see an actual matrix, that is a multi-dimensional matrix. Okay, so in this case we are going to create a 3 by 3 matrix, one for A, one for B, and this happens to be the entries for matrix A and the matrix entries for what, matrix what, B. Remember how we get to what, create matrices, multi-dimensional matrices, that is, we learned this in chapter 1. Okay, so this happens to be the first row separated by a semicolon, the second row separated by a semicolon, and that of what, the last row. Okay, so we use this to generate what, our matrices. So in this case we could have down our matrix as simple as that. So as soon as we have this, we can think of what, adding one these two matrices. Okay, so once we do that, that happens to be our final output. So in this case this is just going to add 4 to 6, 8 and 9, and that is exactly what we are having down here. Okay, that same case we could think of what, subtracting these two matrices. Okay, and that could be done using just that is the subtraction sign. We could think of what, multiplying these two matrices, and remember that that's, as I said before, we could multiply, the number of columns in the first matrix have to be the same as that of what, the second, the row of what, the second matrix. Okay, and you can see this is a 3 by 3, so this satisfies that rule, meaning that we can go ahead to what, multiply these two using only one, the multiplication one operator, without the element wise operator. This time we can just multiply it straightforward. Also, we could also perform an element wise what multiplication. Okay, so this will take the first entry in matrix A and multiply with the first entry in matrix B. Okay, so this one happens to be 2 times 2, and that is the one giving us 4. 4 times 5, that is the one giving us 20. So this is just going to continue until it gets to the last one. So you can see that this element wise multiplication is different from our normal multiplication that we know. Okay, so that is basically the difference. So with this also we could think of doing an element wise division of the two matrices. Okay, so A dot division operator of P, and this is just going to do the division, element wise division for us. Okay, so just as we did multiply the vector by a constant or a scalar, we could also do the same in here, and we could also do an element wise multiplication of a matrix using the scalar. Okay, so in this case we chose a scalar of 3 and we are multiplying 3 by the matrix, and in this case we are performing an element wise multiplication of the matrix by what, 3, and that is basically the same thing. Okay, so with this, let's see how we can perform the dot product of two vectors. Okay, so suppose that we have vector A and vector B, we could perform the dot product of these two matrices, and I believe you guys do remember the formula of how to dot two vectors. Okay, so once we dot these two vectors, this is the answer that we are getting, and with this we use the function dot, that is the dot, then you specify the two vectors, and that is just going to do that for you. In that same way, we can think of what crossing two vectors, that is the cross product. Okay, so in this case we use the function cross, we specify the two vectors, and that is the answer that we get. Okay, all right, now suppose that you should have a sequence of what numbers or in the form of a vector, and you would like to sort this vector. Okay, you could use the function sort. Okay, so in the first instance we are trying to create the vector, okay, using these entries, and once we use the function sort, this is just going to sort this vector from in the form of ascending order, so least to the highest. Okay, so this could be achieved using the function sort. You could also estimate the mean of any vector. Okay, so suppose that we have this vector 2, 3, 4, we could estimate the mean of A using the function using the function mean. We specify the vector that we need, and this is just going to create or give us the mean of the vector. We could also sum entries in the whole vector. Okay, so with this vector we could use the function sum, and this is going to sum all the entries, and we have this to be 91. We could also find the product, okay, more or less like the factorial, or the product. In this case, this is just going to multiply all the entries that we have in a vector. So suppose that we have a vector 2, 3, 4, 5 being assigned to the variable A, we could use the function prod, that is the prod of A, and that is going to give us the product of all the entries we have in there. We could determine the minimum entry in a vector using the main function. Okay, so suppose with this vector we could estimate the minimum, which happens to be 5. Okay, and that is exactly as we see in here. We could estimate the maximum, and that happens to be in this case that happens to be, I think, 23. Okay, so max of A is just going to give us 23. Okay, now in creating matrices, at times there will be the need for us to create a zero or matrix containing what elements to all 0. Okay, and in that case we can use the function zeros, and we specify the dimension that we need, okay, and that is just going to create the matrix that we need, okay. So suppose that I would like to create a 10 by 10 matrix all containing zeros, okay. I could just use just the function 10 and 10, okay. So the first one stands for the row and the next one stands for the column. So once I press enter, this is just going to create a 0 by 10 by 10 in which all the element happens to be what, 0, okay. In that same case, I can create a matrix which contains ones, and in this case I'm going to use the function ones, okay. So once I do this once, in that same case I could create a 10 by 10 depending on the dimension that you need, okay. Once you create 10, they're just going to create that, okay. In that same case, if you should want a 10 by, let's say, 5, they're just going to create as you request, okay. In that same case, you can think of creating an identity matrix. Now, in creating the identity matrix, in this case, we are going to specify the number of our diagonals that we need, okay, and we are going to use the function I, okay. So if I should type in I, in this case, I need a 10 by 10, this is just going to create an identity matrix containing all ones, okay. That is also there. So what if you like to generate a random matrix containing random numbers between 1, 0 and what, 1? In this case, you can use the function rand and just specify the dimension. So rand, so suppose that I should want a 3 by, let's say, 5. I specify that, and this is just going to give me random numbers. That is a matrix 3 by 5, but randomly random numbers between 0 and 1, okay. So that also happens to be there. You could also create a diagonal matrix containing specific elements, okay. So all that you have to do is just create the vector first, then in there you specify use the diag function, and they're just going to create that diagonal matrix as you require, okay. Now for any matrix, you could use this function size. That is, if you are not so sure of the size, you could use the dimension. You could use a size function to determine that. So with this, I just created this matrix here. We call it front. In this case, let me assign the whole of this front to, let's say, matrix B. In this case, uppercase B, okay, as simple as that. So that is our B. So if I'm not so sure of the size, I could just use the function size and I specify B, okay, and they're just going to give me the dimension of our matrix that we created, and that to be a 3 by 5. And remember, we also learned something about getting to see the properties using the whos. And once you do that, you can see that this here is going to give us everything we need, or everything, all the properties about the variables we have in there. In this case, B happens to be what, a 3 by 5, okay. So that is also done. Now with this, if you like to see the length of any vector, that is the number of entries, we could use the function length, and this is just going to give us that. If you like to determine the determinant of any matrix, we could use the function det, okay. So with our matrix that we created, let's see, that is the B. Let's see if you could determine its determinant provided it's not singular, okay. Yes, so you could see that this matrix is not a square matrix, okay. So we should have a problem in there. So with that said, let me try to create let's say a 3 by 3 that is randomly created, and let me try to determine the determinant of B. So that is exactly that we see here. Okay, so the determinant of this matrix B that I just created is the one we just see right here. Okay, with this we could also determine the inverse of any matrix using the function inverse. Okay, so with this, let's try to find the inverse of our matrix B, the one we just created up there. So this happens to be the inverse. Okay, that is that. We could also estimate or transpose this matrix using this operator that we have here. Okay, now this happens to be like a single quotation mark. Okay, so note that. Okay, so if we like to transpose our matrix B, you just have to introduce in that, and once you do that, this is just going to transpose our matrix B for us. Okay, so what if you would like to select elements, okay, extract element within a matrix. Okay, now remember when we were dealing with R, before we can extract any elements from R, we have to use what? The block parenthesis, or should I say the square bracket. Okay, but once it comes to MATLAB, they are more or less like the opposite sides. Okay, now in extracting elements, or let's say in creating elements, we use the square bracket, but if you like to extract, we use the what? The other bracket. Okay, is it the circle bracket or something? Yeah, that bracket. Okay, so suppose that we have this matrix that is with these various entries, that is 12 up to this 24. Okay, and that is exactly as we have in here. Okay, now if you like to extract the element on the third row and on the second column, that is the third row and the second column, so in this case we are looking at this 18. All that we have to do is just specify the matrix, specify the row, and specify the column. So in this case, that is 2 and 3, which is this number, and we are getting exactly this value that we see here. Okay, so going back to our MATLAB, suppose that we have remember our matrix B. This is our matrix B, and we would like to select any entry, okay, or extract any entry. Also, let's suppose we like to extract this entry. Okay, so in this case we have to introduce or just specify the matrix, then open the bracket, then specify the location. Okay, or should I say the position, okay, or the coordinate. Okay, so in this case this is going to be, remember this is on the second row and on the third column, so 2 column 3, and this is just going to give us what? This entry as we are looking for. Okay, so if you like to select any entry, all that you have to do is just specify the position, and MATLAB is just going to give you whatever you are looking for. Okay, now what if you like to select all the elements on a specific row? Now in this case you could use this column. Okay, now this column that you see here refers to everything on the row, or everything. Remember, the first argument happens to be the row, then separated by a comma, then the following is the column. Okay, so if you specify this column in the first part, it means that it should select or should provide you with everything you have on the row. Okay, now in that same case, if you should do same on that of what? The column side, it means it should give you everything on the column. Okay, so in this case, suppose that we need everything on the third column. Okay, it means that we are going to need everything on each row, and with this we are specific on the third column. Okay, so this is just going to print everything, all the rows, but we need all the rows only from the third column. Okay, so once we do this, that is exactly what we are going to get. Okay, and in that same case, if we need everything on a specific row, you could specify the row number and specify everything on that column. Okay, so going back to our MATLAB, suppose that we like to see everything on this second column. Okay, we can specify our B and specify that we need all the rows on a specific column. In this case, we need column 2, and once we specify that, this is just going to give us everything on that. Okay, in that same case, suppose that we like to see everything on, let's say, the third row. Okay, in this case, we need everything on the third row, but everything on that specific column. So we specify this column sign, and once we do that, we get everything that we need. Okay, that is as simple as that. Okay, now with this, let's see how we get to solve systems of linear equations. Okay, now remember that for any system of linear equation, you could generally have it of this form. That is, you should have this first matrix containing only the coefficients, okay, and being multiplied by the entries, or should I say the variables that you are looking at, okay, then finally equal to the solution that you need here. Okay, and remember that we are interested in finding the values for x, y, and z. Okay, so this happens to be that. So this expression that we see here has been rewritten as k times x is equal to what? X, as we see in here. Okay, so for us to determine the value of our x's, or this capital X, all that we have to do is to try to make this x our subject of the equation. Okay, so in this case, we are just going to divide both sides by k so as to move k to the other side of the equal to sign. Okay, and once we do that, our x will be equal to what? The inverse of k times the x. Okay, so this is basically the notation for estimating or finding solution to any system of linear equation in MATLAB. Okay, and in MATLAB, this is being written as x is equal to inverse of k. Remember, this is what equal to what? K inverse, and this k happens to be a matrix. Okay, so we can find the inverse of k and just multiply by the x, and this is just going to give us what? The matrix, the solution that we are looking for. Okay, so suppose that we should have this matrix or system of equation. Okay, now you can see that we have 3a 6b plus 8c is equal to 101.5. Okay, second system and the third system. Okay, now with this, we could extract only the coefficients, okay, and just place them in MATLAB. Okay, and that is exactly as we see in here. Okay, so k is equal to only the coefficient, and that is what has been created as this first matrix. Okay, now the solution, as we have at the right hand side of the equal to signs, is the one that has been created here. Okay, but remember, this is what? A column vector. So all this were separated by the column, okay, as you can see here, and that is exactly what we have here. Okay, so for us to get the solution to a, b, and c, we can do this using the notation. Okay, now remember that all that we need to do is to find the inverse of what? The matrix, and multiply by the solution, and that is exactly what we've done here. Okay, so the inverse of k, which is the one that we have here, times the solution, that is the solution that we have, okay, that is s, and once we do that, we are going to get the actual solutions for a, b, and c, and that is exactly what we have here. Okay, so you could have any let's say any dimension. You could have a 10 by 10 or any huge system that you can come across once you are dealing with your own stuff. Even in the field of engineering, we come across so many unknowns, especially when you are dealing with operations research. You come up with so many a system with so many decision variables just like this, and MATLAB can help you do this. Okay, I know this is somehow difficult to do, like in the case of 4 by 4 and the others. Okay, but with MATLAB, just enter in the function and the solution, and MATLAB is just going to find the unknowns for you. Okay, as simple as that. Okay, so that brings us to the end of chapter 2, and I'll see you guys for chapter 3. Bye for now.